guys, welcome back to Wong Chemistry channel. For this video, we are going to talk about boiling point. We know that boiling point is the point where your solid changing to liquid. Okay, so it's a temperature where the solid is changing to liquid. And we are going to look at the factor affecting the boiling point. And also we are going to predict and discuss the boiling point between different compounds. Okay. We are going to learn on how to determine which compound having higher boiling point and why they are having higher boiling point. Alright? First and foremost, let's look at the factor affecting boiling point. First and foremost, your boiling point will be highly affected by intermolecular forces. And we have two types of intermolecular forces. The first one is your van der Waals forces. The second is your hydrogen bond. It's very important for you to able to identify which one having hydrogen bond, which one having van der Waals forces. And you should always know that your hydrogen bond is always stronger than your van der Waals forces. Alright? When we compare hydrogen bond and van der Waals forces, hydrogen bond is always stronger. When it's stronger, means that you need more energy to overcome the strong hydrogen bond. Therefore, the one that having hydrogen bond will always have a higher boiling point. Vice versa, the compound that having weak van der Waals forces will have a lower boiling point. So when we are comparing hydrogen bond and van der Waals forces, hydrogen bond is always having higher boiling point. Alright? But what happens when we are comparing the molecule only from van der Waals forces? What happens when both of your compound or all your compound is under van der Waals forces? We have three factors affecting that. The first one is your molecular mass. We must always check the molecular mass first if both of your compound or all of your compound having van der Waals forces. Molecular mass is highly affecting the weak van der Waals forces. When the molecular mass is higher, your van der Waals forces will be stronger. Alright, because it's highly affected by the molar mass. When the van der Waals forces is stronger, your boiling point automatically is higher over here. So the higher the molecular mass, the stronger the van der Waals forces, more energy needed to overcome the strong forces, therefore boiling point higher. Make sense? Therefore, we move to the second factor that affecting the van der Waals forces. The second factor is your molecular shape. We will then go for the molecular shape. Alright, but bear that in mind, you can only move from your molecular mass to the molecular shape with one condition. The molecular mass right now is similar. When the molecular mass right now is very similar, you cannot use it as a factor to discuss the boiling point. Therefore, you move from the molecular mass to the molecular shape. Alright, and in molecular shape, we will talk about one important thing, which is your contact surface area. Alright, so what will be affecting the molecular shape is the contact surface area of that shape. Okay, and we have three different shapes that we are going to look at, which is cyclic, that will have the highest contact surface area compared to your straight chain. Okay, and last but not least, your branch molecule will have the lowest contact surface area. And the higher the contact surface area, the stronger the van der Waals forces. And when the van der Waals forces is stronger, boiling point automatically highest because more energy is needed to overcome the strong van der Waals forces right now. Okay, so bear that in mind, in the molecular shape, we will focus on the contact surface area. The higher the contact surface area, the larger the contact surface area, the stronger the van der Waals forces. The stronger the van der Waals forces, the higher the boiling point will be. Okay, and we have three different conditions, which is your cyclic, your straight chain, and your branch. Your cyclic will always have the largest contact surface area. Make sense? And what happens when the molecular mass is similar, the molecular shape also similar? Then we will move on to the last factor affecting your van der Waals forces, which is molecular polarity. If the mass is very similar, even the shape is very similar, then we will look at the molecular polarity. Okay, so bear that in mind, we will only look at the molecular polarity when the molecular mass is very similar, when the molecular shape also very similar, then only we will look at the molecular polarity. So in the molecular polarity, we will definitely talk about the polarity of the molecule. When the polarity of the molecule is more significant, is a very polar molecule, then the van der Waals forces will also be stronger. When the van der Waals forces is stronger, your boiling point will automatically be higher because more energy is needed again to overcome the strong van der Waals forces. Okay, so I hope right now you know which factor you will use for the van der Waals forces. Bear that in mind, we will look at van der Waals forces at the beginning is your molecular mass. If the molecular mass is very similar, then only we will move on to the molecular shape. If the molecular mass and the molecular shape of the molecule both are very similar, then only you move to the molecular polarity. So that is the flow that you will check for the van der Waals forces. Okay? And let's see what happened to the hydrogen bond. Look at the factor affecting the hydrogen bond. Hydrogen bond having two factors affecting. First one, which is electronegativity. Second is the number of hydrogen bond. We know that hydrogen bond can be formed between your H with fluorine, your H with oxygen, or your H with N. That is how your hydrogen bond can be formed in the previous video. We talked about that. Alright? So the electronegativity is definitely comparing the electronegativity of your fluorine. We know that fluorine electronegativity is higher than oxygen and the lowest is nitrogen. Okay? So fluorine electronegativity is number 1, followed by oxygen, followed by nitrogen. That is the first factor, but it's not the only factor. We have a second factor, which is number of hydrogen bond. Obviously, when the hydrogen bond that you can form in a compound is higher, when you can form more hydrogen bond, you definitely need more energy to overcome the hydrogen bond. Since you are forming a lot of hydrogen bond, you definitely need more energy. When you need more energy, that's why the boiling point is higher. So the higher the hydrogen bond that you can form, the more hydrogen bond that you can form, higher the boiling point of the compound will be. So we have two factors affecting your hydrogen bond over here. The first one, electronegativity. The second one, number of hydrogen bond. Electronegativity, knowing that your fluorine is the most electronegative, followed by oxygen and nitrogen. While for the number of hydrogen bond, knowing that the more hydrogen bond you can form, more energy will then needed to overcome the number of hydrogen bond that you form. Therefore, boiling point will be automatically higher. Okay? So I hope this recall a bit about your memory on the first part of this subtopic. Okay? About how the factor is affecting the boiling point. Bear that in mind, the first thing that we will always do is to identify the type of intermolecular forces that you have for your compound, knowing that your hydrogen bond is always stronger. Therefore, the compound that having hydrogen bond will always having a higher boiling point compared to the compound that having weak van der Waals forces. Bear that in mind. Let's go for the first example that I have over here. The first example is comparing the boiling point between HF and your HBr. So knowing that you have your HF over here and your HBr, I think the first step that we will do is to identify the type of intermolecular forces. Obviously, your hydrogen fluoride HF over here having hydrogen bond. Okay? While your HBr over here obviously having only weak van der Waals forces. And from that, you already know which one is actually having higher boiling point, right? Because your hydrogen bond is always stronger than your weak van der Waals forces. So the first thing that we will do, always identify the type of intermolecular forces. Since your HF having hydrogen bond, therefore, you know that hydrogen bond is stronger than van der Waals forces. So when your hydrogen bond is stronger than van der Waals forces, what happened? Simple. More energy is needed to overcome the strong hydrogen bond in hydrogen fluoride. And more energy means what? More energy always means higher boiling point. Therefore, HF has higher boiling point than your HBr. And as simple as that. Therefore, at the very beginning, it's very important to identify the type of intermolecular forces for the compound that you're comparing. If you can identify the type of intermolecular forces for HF correctly and for the HBr correctly, then you can straight away explain the factor that affecting both of the compound in terms of boiling point. Next, for the second example, we are comparing the boiling point of HF again, but in this, we are comparing the HF that I have over here with ammonia and H3. So let's take a look. So right now, I have my HF, I have my NH3. Knowing that my HF, we talked about that just now, HF having hydrogen bond. And your ammonia over here, NH3, also having hydrogen bond. And bear that in mind when we are talking about boiling point. The hydrogen bond that we are talking is the hydrogen bond formed with itself, with the same molecule. Alright? Because we are talking about boiling point, we are not talking about solubility. So the hydrogen bond must be formed within the same molecule. So the problem arises right now is both is having hydrogen bond. So when both is having hydrogen bond, then you need to recall hydrogen bond is affected by what factor? Hydrogen bond is affected by the electronegativity as 1. And then the hydrogen bond is also affected by number of hydrogen bond. Remember that? And over here, which factor are we going to discuss? Simple. Looking at it, your hydrogen bond in HF is between hydrogen and fluorine. The hydrogen bond in ammonia is between hydrogen and nitrogen. So over there, we will definitely go for electronegativity. And we know that your fluorine is the most electronegative compared to your oxygen, compared to your nitrogen. So which one will have higher boiling point? And why the compound is having highest boiling point? Simple. Over here, we are going to talk about electronegativity. Fluorine is more electronegative than nitrogen. Okay? That is the first thing because we are comparing the HF and the NH3. When fluorine is more electronegative than the nitrogen, what happens is the hydrogen bond that you form in the HF will be stronger. When the hydrogen bond formed in the HF is stronger than the one in your ammonia, simple, we always then follow up by the sentence of more energy is needed to overcome the strong hydrogen bond. And when more energy is needed to overcome the strong hydrogen bond in HF, then automatically HF has higher boiling point than ammonia. As simple as that. Easy? That is how we are going to compare the boiling point between the compound. Okay? And in here, we are going to talk about the electronegativity between the fluorine and nitrogen. And the higher the electronegativity, the higher the boiling point because the stronger the hydrogen bond will be. The next example that we are going to look at is we are going to compare again the hydrogen fluoride, your HF. But in this example, we are comparing the HF with our water molecule. Okay? Knowing that your HF over here and your H2O over here, both are having hydrogen bond. Okay, and bear that in mind, since we are going to talk about boiling point, therefore the hydrogen bond that we are going to talk about is the hydrogen bond formed with itself. Alright, we are not talking about solubility. So the hydrogen bond means between HF and another HF that is hydrogen bond. Okay, same goes to your water. The hydrogen bond that we form in the water molecule is the hydrogen bond formed between the water molecule. And the same thing, since both is talking about hydrogen bond and knowing that your hydrogen bond has two factors, your electronegativity and also the number of hydrogen bond that can be formed. So which one are we going to talk about? Over here, it's quite obvious we are comparing between your HF and your H2O. Although we know fluorine is more electronegative than your oxygen, than your nitrogen, so talking about electronegativity, your fluorine will be champion. Okay, your fluorine will have a higher electronegativity. But you also need to look at the molecule. So right now, if you're having HF and your HF, your hydrogen bond can be formed between this. But when you have a H2O, guys, when you're having a H2O, you can form more hydrogen bond over here. Alright, you can form more hydrogen bond over here. Okay, so when you can form more hydrogen bond in the water, the number of hydrogen bond is the factor that we will use to discuss the boiling point between HF and H2O. Although fluorine is more electronegative than oxygen, but in H2O, more hydrogen bond can be formed. Okay? And since more hydrogen bond can be formed in the water molecule, thus more energy is needed to overcome the hydrogen bond formed in water. Okay? And when more energy is needed, automatically your H2O has higher boiling point than your HF. Okay? So when we are comparing your HF and your H2O, the factor affecting is not about electronegativity but about hydrogen bond. Bear that in mind, both of them can form hydrogen bond. So when we say water can form more hydrogen bond, make sure you have the word more is written clearly. Okay? In your water molecule, your hydrogen bond, there will be more hydrogen bond can be formed. Therefore, more energy is needed to overcome the hydrogen bond that formed in water molecule. Thus, water will have a higher boiling point than your hydrogen fluoride. Simple, easy. So again, that is how we choose the factor affecting the boiling point. Another example, I have example 4 over here. We have our CH3CH2OH and also we have our ether. So we are comparing our ethanol, alcohol, and also our ether over here. Okay? So as always, the first thing, what will I do is I'm going to identify the type of intermolecular forces. Knowing that the presence of OH will definitely give rise to the hydrogen bond. Alright? So in the ethanol, within ethanol, ethanol can form hydrogen bond with itself. Alright? All the OH can form hydrogen bond with itself. But your ether over here, CH3OCH3, your ether over here cannot form hydrogen bond with itself. Your ether can only form van der Waals forces with itself. Alright? And when we are comparing hydrogen bond and van der Waals forces, I think the explanation will be quite simple and clear. The sentence of hydrogen bond is stronger than weak van der Waals forces is always needed. Okay? And whenever we say the hydrogen bond is stronger than van der Waals forces, and before you say that your ethanol is having higher boiling point, why higher boiling point? Always because you need more energy to overcome the strong hydrogen bond. Make sure you have all the explanation nicely written down. And whenever you have more energy is needed in the particular compound, that compound will definitely having higher boiling point. So in this case, your ethanol CH3CH2OH will have a higher boiling point than your ether. And as simple as that, by only knowing your hydrogen bond is stronger than van der Waals forces. And what more important is knowing that your OH can definitely form hydrogen bond with itself, while your CH3OCH3 can only have weak van der Waals forces with itself. And therefore, it's very important to determine the intermolecular forces between both of them. Okay? Next, let's go for example 5 that we are comparing your SO2 and your SO3. And from the question itself, you can see sulfur, oxygen, obviously no hydrogen bond. Both of them will be only talking about van der Waals forces. So your SO2 and your SO3, both of them are only having van der Waals forces. Bear that in mind, van der Waals forces, your W is a capital letter. Your V and your D is all small cap, while your W is a big cap over here. That is how we write van der Waals forces. Okay? So both of them can form van der Waals forces with themselves. And talking about van der Waals forces, we know that we have 3 factors affecting van der Waals forces. But the first factor is definitely molecular mass. Alright? And looking at your SO2 and SO3, without calculating the molar mass, you already know that your SO3 will have a higher molar mass. Why? It's the same sulfur, but oxygen in SO2 is only 2 oxygen, but SO3 having 3 oxygen. Automatically, molar mass of SO3 is definitely higher. And since the first factor that affecting the van der Waals forces can already differentiate them, it's not needed to check the second factor because molecular mass is already different. Straight away, you can explain by using the factor of molecular mass. Okay, so molecular mass of SO3 is higher than the SO2. When the molecular mass is higher, what happened to the van der Waals forces? Van der Waals forces become stronger in SO3. And whenever the forces is stronger, we know that the boiling point is higher. But why when the forces is stronger, the boiling point is higher? Because more energy is needed again to overcome the strong van der Waals forces. And whenever more energy is needed to overcome the strong van der Waals forces in SO3, straight away, ladies and gentlemen, SO3 has higher boiling point. So that is how we actually get your SO3 having a higher boiling point, knowing that both of them can only form van der Waals forces with themselves. Therefore, the first factor affecting your van der Waals forces is your molecular mass. Knowing that your SO3 and your SO3 having a higher molecular mass. When the molecular mass is higher, the van der Waals forces is stronger. Therefore, more energy is needed to overcome the strong van der Waals forces. SO3 have higher boiling point. That's it. As simple as that. Easy. Next, we are going to look at your example 6. We are still comparing the boiling point, but we are comparing 3 compounds. We are comparing your cyclobutane, your butane, and also your 2-methylpropane. Okay? So that is how your cyclobutane, butane, and your 2-methylpropane look like. Alright? And if you look very, very carefully, guys, all 3 of them are actually having a similar molecular formula. Your cyclobutane having a C4H8, while your butane is actually having C4H10. Same goes to your 2-methylpropane also having C4H10. All 3 of them are having a similar molecular formula. And this similar molecular formula is telling you what? This similar molecular formula means that they are having a similar molecular mass. Why? Because the difference is only on the hydrogen. All of them have 4 carbon. Okay? So 4 times 12, you have 48. And the mass is only differed by 2 hydrogen over here. Therefore, all 3 of them are actually having similar molecular mass. And also, looking at your cyclobutane, butane, and your 2-methylpropane, all of them is carbon and hydrogen. Therefore, we don't have any hydrogen bond. All of them will also have van der Waals forces. And when we are going to talk about van der Waals forces, guys, we know that van der Waals forces is highly affected by the first factor, which is your molecular mass. And right now, the problem arises is your molecular mass cannot differentiate them. because the molecular mass is very similar. So what happened is, when the molecular mass is very similar, we then move to the second factor, which is molecular shape. Remember that? So your molecular shape having three conditions. Alright, if you remember the three conditions, they are cyclic, which have the largest contact surface area. Next, you have your straight chain. Your straight chain is the second largest contact surface area. Last but not least is your branch molecule. Your branch molecule having the lowest contact surface area. And looking at the compound that I give to you, obviously that is your cyclic. Can you see the cyclic? Alright. And that is obviously my straight chain. And last but not least, this compound that having a branch, that is obviously your branch molecule. Since the molecular mass is similar, therefore we move to the molecular shape. And the molecular shape can already differentiate them. Do you need to go for polarity? No, we will stop at molecular shape because we already can differentiate them. So in this question, we are going to talk about molecular shape. And whenever we talk about molecular shape, guys, there is one thing that you must mention: contact surface area. The molecular shape is highly affected by the contact surface area. Okay? So first and foremost, your explanation must start with the similarity that you have, the molecular mass and van der Waals forces. The second, we go for the criteria. So we are going to talk about your cyclobutane having what type of molecular shape. And once you have mentioned the differences between them, we are going to discuss the differences, alright? And since we agree to use the factor affecting its molecular shape, therefore the main thing in molecular shape is the contact surface area. So discuss the contact surface area between cyclic, straight chain and branch molecule. And why when the contact surface area is largest, the boiling point is higher? Simple. When you have a large contact surface area, the area for the van der Waals forces to form is larger. So when you have a big area, more van der Waals forces can be formed. Alright? So when more van der Waals forces can be formed, straight away van der Waals forces will be stronger. Compared to the branch molecule. Compared to the branch molecule, when you have branch, it's very compact. Alright? When the branch molecule is very compact, the contact surface area becomes smaller. Okay? And as always, when the van der Waals forces is stronger, you definitely need more energy to overcome the strong van der Waals forces. And therefore, as a result, your cyclobutane has the highest boiling point, followed by butane and 2-methylpropane. Okay, so remember, when all of them are having van der Waals forces, the first factor that we check is molecular mass. If the molecular mass is very similar by looking at the molecular formula, alright, then we will move on to the molecular shape. Okay, you cannot discuss molecular mass anymore in here because they are very similar. So you move to the molecular shape. The biggest fans in molecular shape is contact surface area. Whenever we talk about molecular shape, we always talk about contact surface area. And the larger the contact surface area, the stronger the van der Waals forces. The contact surface area have three different types. The cyclic, which have the largest contact surface area, followed by the straight chain, followed by the branch. And when the stronger the van der Waals forces, more energy will be needed to overcome the strong van der Waals forces. As a result, your cyclic, your cyclobutane over here, will have a higher boiling point compared to your straight chain, compared to the branch molecule. Okay? And all this is how we determine the boiling point of your compound. Easy. The last example of this video, compare the boiling point of Br2 and ICl. And as always guys, we start off with the type of intermolecular forces, your Br2 and ICl. So quite obvious, both of them don't have your F, O or N, because F, O or N is the things that will form hydrogen bond. Since both of them don't have, automatically both of them will be holding van der Waals forces. And since both of them having van der Waals forces guys, then we will check the factor affecting your van der Waals forces. Bear that in mind, van der Waals forces is highly affected by molecular mass. So let's check the molecular mass of the Br2 and ICl. Your Br2 over here, the molar mass is approximately 159.8 gram per mole. Okay, while your ICl is approximately 162.4 gram per mole. Alright, so looking at the molar mass, you can see that one is about 159.8, another one is 162.4. The molecular mass is also very similar in this case. When the molecular mass is very similar, then we go for the second factor, which is molecular shape. So let's check the molecular shape of the Br2 and ICl. Your Br2 looking something like this, which is a linear. Your ICl also looking something like this, which is also a linear. The molecular shape is also very similar right now. And when the molecular mass is also similar, molecular shape is also similar, guys, we don't have any other factor. The last one will drop on the polarity of the molecule. So in this question, we cannot talk about molecular mass, we cannot talk about molecular shape, but we can talk about the polarity between your Br2 and also ICl. Alright, obviously your Br2 is a non-polar molecule. Well, your ICl, because your I and chlorine is more electronegative. Therefore, the bond dipole is towards chlorine, the dipole moment is also towards chlorine. And the mu will not equals to 0 because it's a polar molecule. Alright? And talking about your non-polar molecule and your polar molecule, knowing that your non-polar molecule is having London forces. While your polar molecule over here, obviously having dipole-dipole forces. Okay? And quite obvious, your non-polar molecule in the London forces, you have a temporarily dipole moment. Remember that? While in the polar molecule, which is a dipole-dipole forces, you have a permanent dipole moment. So which one is stronger? Which one need more energy to overcome? Which one will have higher boiling point? Obviously, the permanent is stronger. Okay? So when the permanent forces is stronger over here, therefore, more energy will be needed in here. And when more energy is needed to overcome the strong van der Waals forces, in here, straight away guys, which one having higher boiling point? Obviously, the one that having permanent dipole moment, the one that will form stronger van der Waals forces. Therefore, over here, higher boiling point is for ICl. Because ICl and your Br2 both are having similar molecular mass and also similar molecular shape. So the only factor that can differentiate them is the polarity. Your Br2 is a non-polar molecule. Your ICl is a polar molecule. And over here, polar molecule will have a higher boiling point because they are forming a permanent dipole, which is stronger than the temporary dipole and therefore need more energy to overcome the permanent dipole moment. Okay, and whenever more energy is needed, you're definitely having a higher boiling point. And as I say, this is the last example, so that's it for this video. If you have any question regarding boiling point or having any molecule or compound that you want me to compare, drop it in the comment below and I'll get back to you as soon as I can. I hope this video able to help you to predict which compound is having higher boiling point and also able to help you to understand which factor that we are going to choose to discuss the boiling point between your question. Okay? And of course, remember to like the video, subscribe to my channel, and also share it with your friends. Thank you for watching, and I'll see you again in the next video.